Okay, thank you very much. So this is the follow-up of the lecture of yesterday. Yesterday, we have seen that when planets are born in a protoplanetary disk, it tends to move, it tends to migrate. And today, we study how different planets that are migrating interact with each other. And then what happens once the disk goes away. So we are considering a case first of convergent migration. What is convergent migration is when by migration, the outer planet is approaching the inner planet. So this happens in three cases, basically, because we have seen yesterday, type 1 migration is proportional to the mass of the planet. So if you have a low mass planet and a bigger mass planet, this one is migrating at a given speed. This other is migrating faster, so they are approaching each other. This is an example of convergent migration. But we have also seen that at the edge of the protoplanetary disk, there is a planet trap. So you can have a major planet that migrated here and stopped because it's at the planet trap. And then you have a smaller planet that is still migrating. And this is, of course, also a case of convergent migration. And the third case is when you start to have a planet, a giant planet, so which opens a gap in the disk. And this migrates much more slowly than a planet that is less massive but does not open the gap in the disk. So these are all cases of convergent migration. And so what we are going to see here is what happens, and then we try to explain what happens. So here we see the two planets, the interior planets and the outer planet. And this is the orbital eccentricity. Initially, the two planets had circular orbits. And in this movie, we are renormalizing the units of distance from the star so that the inner planet is always at 1, because we renormalize the units. Doesn't mean that the planet is fixed, but we watch the motion of this planet relative to this planet. So we start the movie and you see that, okay, there is my convergent migration. The black planet is approaching the red planet. You've also seen that initially the eccentricity were not really 0, but they damped down. And then, look, this is what happens. At some point, the planets stop approaching each other, and instead their eccentricity rises until they reach an equilibrium, and then nothing moves anymore. It's not that the movie has stopped, it's not stopped yet. So you see the planet has lightly blinking, but we are at an equilibrium condition, and so now the movie stops. And so nothing moves anymore. So my goal is to explain what happens. So this is called capturing resonance, because this dashed line where all the action happens is actually a resonance. In this case, the 3-2 resonance that occurs when the period of the outer planet is 1.1.5 times, 3/2 times the period of the inner planet. Now, explaining resonances is a tricky business. And the real way to do it is to develop a lot of mathematical formalism in Newtonian dynamics. In a lecture of 1.5 hours, this is not possible and would lead to failure. So I will avoid all mathematical formalism, and I will try to explain what happens with my hands and little drawings and schemes. Of course, it's far from rigorous. Somebody wanted a rigorous lecture on Hamiltonian dynamics, resonant Hamiltonian dynamics. It will be disappointed, but probably the others can follow a little bit better. So let's try to see what happens. First of all, what is a resonance? So this is an example of a 2-to-1 resonance, when the orbital period of the outer planet is twice the orbital period of the inner planet. And for simplicity, the inner planet is on a circular orbit and the outer planet is on an elliptic orbit. So the movie, the planet started in conjunction. This planet travels faster than the other one, twice the speed, resonance. And so when it makes the first orbit, the other one has made half an orbit. And when the outer planet has made a full orbit, the inner planet has made 2 orbits, and the 2 bodies come back to the initial configuration. So in principle, already, a resonance, what is it? It's the periodic orbit, because the situation, the configuration repeats after 2 orbits of the inner planet, 1 orbit of the outer planet. So resonance is periodic orbit. And when you are exacting resonance, and then the conjunction between the 2 planets is the minimal approach distance of all the configurations that the planet had relative to each other during their motion. This is the configuration where they are minimal, they are distancing minimal, and so their gravitational influence is maximal because the gravitational force is proportional to the inverse of the square distance. Now let's see what happens if the planets are not quite, almost in resonance, but not quite. So the outer planet is slightly outward of the rest. So we start the movie as before. By eye at the beginning, you don't see anything particularly different from what happened before, but you can see that, well, when the first planet closes the orbit, the second one is a little bit behind. And then, for this reason, when the planets are in conjunction, well, the orbit is not. So because we are slightly out of resonance, this is no longer a periodic motion, no longer a periodic. And the important consequence is that the minimal approach configuration does not happen when the planets are in conjunction, but happens a little bit before. And so this is this line between the sun and the outer planet, and this is the configuration of minimal approach. And so this is the configuration when the interaction between the 2 planets is the strongest. And as you can see, so it's not directed, this force, this gravitational force that planet 1 exerts on planet 2 is not directed towards the sun. So what does this mean? It means that this force, as first is directed towards center, not exactly towards the sun, but still has a strong radial component, when the outer planet is still going out, because it's in an eccentric orbit and has not reached aphelion yet. So you are exerting so the planet is moving out, so has a positive radial motion, but it receives a force with a radial component directed towards the sun. So the positive radial motion of the planet is slowed down, which means that its orbital eccentricity has to decrease. If the planet is going out and is slowed down in its radial motion, the eccentricity is decreased. On the other hand, because this force is not directed exactly towards the sun, there is a tangential component in addition to the radial component. This tangential component is in this direction. So has an azimuthal component that is negative, so a negative torque. So the azimuthal speed of the planet is also slowed down, which means that also the semi-major axis of the outer body has to be. So if we represent the planet like this, so this is our planet on a circular orbit, this is our planet on an eccentric orbit that we said is slightly outside of resonance, because the orbit does not close and the minimal approach configuration occurs before the alignment, then as we've seen, the force causes a net decrease of the eccentricity and a net decrease of the semi-major axis. So the orbit of the outer planet will tend to move in this direction, like this black arrow, decreasing the eccentricity, decreasing the semi-major axis. Now let's take the opposite case when the outer planet is slightly inward of the rest. So now it's moving a little bit faster than half of the speed of the inner body. So you see that when this has done half an orbit, the inner planet has not done really an orbit. And then when the planet closes its orbit, the other planet is not in position yet. So again, so we stop the movie when the planets are in alignment, are in conjunction. And as you can see, like before, we don't have a periodic configuration. Right? Planet started from here. Like before, the minimal approach configuration is not during the conjunction, but it's a little bit after conjunction. So the maximal force that planet 1 exerts on planet 2 is directed like this red arrow. that has a radial component and also an azimuthal component. Now, the situation is different because the planet is going from, the outer planet is going from aphelion to perihelion. So has a negative radial motion and has, so it undergoes a force which has a negative radial component. So we are accelerating the negative, the radial motion of the planet, which means that the eccentricity of the outer planet has to grow. And the azimuthal component of the force now is directed outward, so it's a positive torque in the direction of the motion of the planet, which means that we are accelerating the azimuthal motion of the planet, which means that the semi major axis also will increase. So going back to our previous representation, if the planet, the outer planet is here, just inward of the resonance, now the force exerted by the first planet tries to change the orbit of the planet in this direction, so increasing both eccentricity and inclination. So what happens close to a resonance is that you have an oscillation around the resonance. You're not exacting resonance on the line, you oscillate back and forth around the resonance on a line that is slanted in this diagram, so major axis versus inclination. This is important. So you keep oscillating like this. Now, this oscillation can have a maximal amplitude, and this is understandable because if you are too far from resonance, then the configurations of minimal approach are all over the place, and you have no the effects don't accumulate. So there is a maximal amplitude of oscillation around the resonance, and this yes, it's more or less symmetric. We will see diagram later, but it's more or less. And it's like a pendulum around the feather. You can actually write the local equations in the form of a pendulum in the good coordinates. It is perfectly similar. And this amplitude has to be null at zero eccentricity, because if you have zero eccentricity, then of course every conjunction is the minimal approach distance. So there is no lever arm to pull on the outer orbit. So we can heuristically, qualitatively understand that the region of space concerned by a resonance has to have a width which has more or less a V shape. So a resonance is thin at low eccentricity and it's wide at large eccentricity. And this is true for all resonances. It's not exactly a V with straight borders and so on, but it's always bigger and at larger eccentricity than at lower eccentricity. So this is my very first heuristic description of how resonance is. Now let's try to go a little bit below. So we have seen that the dynamics occurs on these lines that are actually curves, not straight lines, but which are slanted in some major axis versus. So we can try to represent the resonant dynamics going on this surface. And this is the way to do it. So the natural coordinates are the eccentricity, because as you are moving on this surface, the eccentricity changes. So the radius, the radial coordinate in this diagram will be the eccentricity. And then there is an angle which plays a privileged role in the resonance, which is called the critical angle of the resonance, which is this one. So lambdas are the mean longitudes of the planet, the angle that gives the orbital motion of the planets around the sun. And here we are in a k over k minus 1 resonance. That means that when the inner planet makes k revolution, the outer planet makes k minus 1 revolution. So that means that the speed of lambda prime, which is the orbital motion of the inner planet, is k over k minus 1 times larger than the speed of lambda, which is the mean motion of the outer planet. So at exact resonance, this angle k lambda minus k minus 1 lambda prime does not move. It's a fixed angle. And then you have to add the longitude of perihelion of the planet for symmetry reason, invariance of the equations. So here we are on a surface that is not exactly the resonance. So this angle is not zero, right? It's not fixed. It will move. And because we are outside of the exact resonance, lambda will be too slow. So this combination of angles turns with a negative derivative, which is a clockwise rotation. So this angle is the angle in this diagram. Right? And so on this surface, on this level, which is not really in resonance, the dynamics is simply made of circles, right? Which means that as this angle is rotating clockwise, the eccentricity is not changing much, if not at all. And there is an equilibrium point here at the center, which is almost at eccentricity equal to zero, but not quite. It's slightly misplaced from zero. And so let's report to where it is. It's here, very low eccentricity. Now let's change of level, let's change of surface, and let's go to a surface that intersects the resonant location. And this is the new diagram in the same coordinate, changed a lot. So now the equilibrium point is no longer at zero eccentricity, it has moved from here to here. And so in this diagram, it moved from almost zero eccentricity to higher up. And there is a critical curve that appears. You see, there is this curve, strange curve that intersects itself. It's called the separatrix. It's a critical curve in the diagram and separates the region where the orbits librate around the equilibrium point with this sort of banana-shaped curves, and the region where the orbits circulate, so the other direction actually, or around this equilibrium point. So this separatrix crosses this axis in 2 points, here and here, that we can report on this diagram. So then you can wonder, okay, but this diagram has changed so much. What happened in between? So we can, there is a drastic change in the dynamics by changing the level by not too much, but we can, of course, zoom in and see what happens in intermediate levels, so to understand how we go from here to here. And actually, the first thing that happens is that this figure deforms. It's still made, there is no separatrix, but the equilibrium point moves away from zero eccentricity. And then there is a bifurcation. So another equilibrium point appears, which is unstable, and this critical curve appears like that. And then this critical curve makes a loop here. It will become this loop here. This is how we go from this diagram. And all in levels that are intermediate between this one. And then we change of level, we go to a higher level, and this equilibrium point, the dynamics remains the same, but the equilibrium point moves at higher eccentricity, and this coordinate is simply the banana-shaped orbit look more squeezed, and still the separatrix crosses the axis at 2 eccentricity values that we can report, and then again we can do the same exercise on it. So summarizing, a resonance of this kind, which is called the first order resonance, because the difference between this index and this index is 1, is characterized by a locus of equilibrium points or resonant equilibrium points, which is curved like this. These are our levels that are not, as I said, a really straight line, sort of curves, and are associated with the total angular momentum of the system. And the separatrix does not really join like a V, as in my first drawing before, but is born all of a sudden. So here there is no separatrix. Here the separatrix is born, already open. And these are the faces of the separatrix in this space. And if there are perturbations, short period perturbations, the separatrix become actually chaotic bands. But and inside there is it's the actual resonance. Okay, so now we know how the resonance is shaped in semi-major axis versus eccentricity, or ratio semi-major axis versus eccentricity. We can try to understand why planets are captured in resonance. So This is my resonance with my levels and my separatrices, which are open. And the planet is approaching, outer planet is approaching the inner planet with zero eccentricity or some eccentricity, doesn't really matter. So it comes, approaches the resonance, and when it feels the resonance, it starts to vibrate. It will move on this surface across the resonance as the resonance wants. But at the same time, there is this force that makes the planet to move forward, right? But the resonance keeps acting on the planet, so pulls the planet back in a new vibration on the new level. But the migration forces move the planet towards the sun, but the resonance forces it to make a new vibration, and then so on and so forth. So what happens is that the planet, on average, stops approaching planet 1 and starts to vibrate around the resonance and go up in eccentricity. This is the result of the combination of vibration and motion to the left. Vibration and motion to the left. Vibration is sometimes down, sometimes up, depending if you are outside of the exact resonance or inside. And you combine this drift towards the sun, and this is what happens. So that's why we've seen in the movie that the planet which was moving towards planet 1 at some point stopped its motion and its eccentricity went up. At the same time, we know that from yesterday that the disk not only forces the migration of the planet towards the sun, but also exerts an eccentricity damping. So the resonance is converting the migration into an eccentricity rise. But then you have a competition between the eccentricity rise, that is the migration converted by the resonance, with the eccentricity damping that the disk exerts on the planet directly. And because the eccentricity damping from the disk is proportional to the eccentricity, so the eccentricity damping was minus E over tau E, you know, the more the planet become eccentric, the stronger is this damping force. So at some point you reach an equilibrium. And that's why the the rise of the eccentricity stops. And this is exactly what we've seen in the movie. So movie sort of explains. And the same if you have convergent migration in the other direction, right? So you remember that this is a normalized coordinate. So this can be the case where the bigger planet catches up with the small planet in normalized coordinates with the outer planet. The small planet is moving out. And it's the same scheme. Just we can try to be a little bit less heuristic, go back to our diagrams, and to understand what happens in the capture or in resonance, we can use a principle of dynamics, which is called the adiabatic principle. The adiabatic principle says that if the dissipation, so the migration is low compared to the orbital, to the motion in the resonance, so the libration period, then when the body under the dissipation, the migration moves from one level to the other, the evolution follows a trajectory that encapsulates in these coordinates the same area. So for instance, if away from the resonance, I have a small eccentricity, so my orbit is this one and encapsulates this small area around the equilibrium point. When the planet reaches this level, it will have to be on one of these orbits. Which one? The one that encapsulates the same area that I had at the beginning. I hope we've done the drawing correctly. And then when it moves from this level to this level, again, there are many orbits that we can choose from. And the trajectory that we have to choose is the one that still has the same area. This is the adiabatic. And because far away from the resonance, the planets are on circular orbits because the disk damps the circular orbit. The planets come in very close to the zero eccentricity. So initially, they have very small area, and they have to preserve this small area. So if you go to our scheme, so the planet is approaching from far at zero eccentricity. So the area around the equilibrium point is very small, and this area is kept small. So that means that the planet follows the equilibrium, the locus of equilibrium points, which is this curve. And so as approaches the resonance, the eccentricity has to rise because this is the locus of the resonance. And again, so this eccentricity rise is eventually counteracted by the eccentricity damping from the disk. So it's what I showed before, with hands a little bit more precise. Okay, so are we always captured in resonance? Eventually in some resonance, but not necessarily in the first resonance you encounter. And there are several reasons for failing resonance capture. The first one is the break of the adiabatic principle. As I said before, the adiabatic principle holds as long as your migration is low compared to the libration in the resonance. So the libration period in the resonance has this form. So it's extremely fast, small eccentricity, because we are talking about resonances of order 1, which are those which are the most important in this business. So I will not consider the others. So the libration period is extremely, the libration is extremely fast. So the libration period is extremely slow. It's extremely small, it's a small eccentricity. Then it rises up, and then the libration period decreases again when the eccentricity is big enough. So that means that as I attempt my resonance capture, so I attempt to follow the resonance locus, the eccentricity goes up and the libration period increases. So I can reach a point where the libration period is equal to the time to cross the resonance width. And when this happens, the adiabatic principle is broken. My simple sketch is broken as well, because it means that, you remember my simple sketch was that in resonance, so the planet was trying to making a libration, then moving inward a little bit, then making a libration back, then moving inward a little bit. But now it's moving inward at the same rate as the libration. So the planet, as it librates in, it also moves, so it escapes. And this is so the point when the planet escapes and is not trapped in the resonance. So you see a temporary capture, then the eccentricity grows enough, and then the adiabatic principle is broken, and the planet leaves the resonance and out of the resonance, so keeps migrating again towards this, the inner planet, and its eccentricity is damped by this. So having skipped this resonance, the planet will encounter the next resonance. So let's say this is the 2-to-1 resonance, then it will migrate in and reach the 3-to-2. And the 3-to-2 resonance, so as we approach the two planets, is characterized by a same shape for the libration period, but everything is fast. So the new resonance, so this was 2-to-1, say k equal to 2, and now the k is equal to 1, now k is equal to 2. So this is the 3-to-1 resonance. So that means that the planet will again be captured, go up to somewhat higher eccentricity, but then again, the libration period and the migration time across the resonance will become equal, and the adiabatic principle will be broken, and the planet will leave again. So missing the 3-to-2, if we try to go into the 4-to-3, and the 4-to-3 has the same kind of function for the libration period, but faster now. And now you see that for any eccentricity, the libration period is smaller than the time to cross the resonance by migration. So now in this new resonance, the adiabatic principle will always hold. And so in this new resonance, the planet will be captured forever. So it's a function of how fast you migrate. So you move this line up and down. If you migrate slowly, it takes a long time to cross the resonance. If you migrate fast, it takes a short time to cross the resonance. The dynamic chooses in which resonance it can go. We skip all the first resonances until it goes into a resonance that is close enough, where the index k is high enough, can be 3-to-2, 4-to-3, 5-to-4, 6-to-5, and so on, where the adiabatic principle always holds, and then the capture is permanent. That's how the planets choose which resonance. There is no capture in case of divergent migration. So you can have a divergent migration, for instance, if you are in the opposite situation, right? You have a bigger planet and a smaller planet in type 1 migration. This one moves faster than this one. So in relative terms, these two planets are divergent. In divergent migration, there is no resonant capture possible. And this is easy to understand with my scheme. If the planet is moving out, so it comes out, it hits the separatrix, it makes a libration, and it is on the other separatrix and keeps migrating it out of the rest. So no capture possible. There are more subtle criteria for instability. You can fail capture if the damping is too strong. And the reason is the following. So if you have no eccentricity damping from the disk, which is the theoretical situation, this is your resonant diagram. And as we've seen, the motion in the resonance is like this, which means that the resonance tends to excite the eccentricity in this lower part of the diagram and reduce the eccentricity in the upper part of the diagram. If you have an eccentricity damping, the resonant portlet is rotated like that. It's rotated in this direction. Why? Because at the equilibrium point, because we have an E damping, an eccentricity damping from the disk, the equilibrium point has to shift in a region of the diagram where the resonance would give an eccentricity rise that can counteract the eccentricity damping. That's my only chance to have an equilibrium point. And so the only way to make this is that the resonant diagram rotates. And it rotates more and more, the stronger is the eccentricity damping. And if the eccentricity damping is too strong, this equilibrium point will reach this axis. And then if it's even stronger, it would try to go in this part of the diagram. But then the push becomes weaker. The push in the eccentricity becomes weaker. And then there is no capture, no stability possible. This has been highlighted in this recent paper by Konstantin Batygin and Antoine Petit. And this shows, for instance, what happens for two planets that are migrate towards the 3-2 resonance. And in this case, the eccentricity damping is 1,000 times the semi-major axis damping. First, are these numbers crazy? I said yesterday that the disk gives us, so the disk gives a migration that is proportional to the scale height of the disk to the power -2, but the eccentricity damping is proportional to the scale height of the disk to the power -4. So the ratio between the eccentricity damping and the semi-major damping, so this ratio here, is of the order, again, of h to the aspect ratio to the power 2. The typical aspect ratio in the disks is between 0.02 to 0.05, up to 0.1 even, maybe, if you are really in the outer part of the disk. So you do the square of this, and you get a function of, sorry, -2. So, and you get a ratio of 100 if the aspect ratio is 10%. And you get, if this is 0.03, you get a ratio of 1,000 if the aspect ratio is 0.03. So the actual eccentricity damping compared to the semi-major axis damping is between typically 100 and 1,000. In this case, they assumed 1,000. And this is the semi-major axis migration time scale for different simulations from slow 80,000 years, past 5,000 years. And this is how the capture proceeds. So when capture occurs, the eccentricity grows until an equilibrium point is reached. As you can see, the equilibrium point is not reached on this axis, but is shifted for the reason I explained. And the faster is the migration, so also faster is the eccentricity damping, because the ratio between the two is always 1,000. Then you see that this equilibrium point is shifted more and more until it reaches the vertical axis, which is the farthest it can go. So that means that if you migrate even faster than this, you cannot be trapped in resonance. This is your limit. And in this other diagram, the ratio between the eccentricity damping and semi-major axis damping is 100. So, and the capture induces some oscillations, and you can see, but the result is always the same. The equilibrium point shifts, and if you migrate too fast, at some point you escape from resonance, and then you start to circulate. So you fail the capture in 3 to 2, and eventually will be captured. In the simulation, the bodies are captured in 5 to 4. So if you have too strong of a damping, then you can skip the resonance and go to a resonance where the planets are closer. The last reason to fail capture is called the overstability. So let's see what happens. Overstability works if you have a convergent migration where the inner planet is less massive than the outer planet. So we are in this situation. So we have an inner planet inside, the outer planet more massive. So this planet moves faster, it catches up the small planet, so it's a capture from the interior. And this situation can lead to an instability. So let's see what happens. Again, the coordinates are normalized to the position of the more massive planet. So we see the small mass planet be captured in resonance. The planet go up in eccentricities like before. You see that this planet is less massive than this one because its eccentricity is bigger. But you see that now we don't reach an equilibrium where the movie seems to stop, but doesn't stop. But actually the planets start to oscillate more and more, and oscillate more and more until the inner planet escapes from the resonance and keeps migrating towards the outer planet. So we have a resonant capture for a while, then an increase in the amplitude of oscillation, in the amplitude of vibration in the resonance, that eventually leads to an escape. This is called overstability. And it's relatively easy to understand what happens with my scheme, a heuristic scheme. So the body goes in, it's captured in the resonance, as I said. So it migrates, migrates back, it migrates, so it goes up until the eccentricity damping blocks the rise of the eccentricity. And this is what we've seen in the movie. So when we reach the equilibrium and the planet eccentricity doesn't grow anymore, still something is not completely balanced out. Remember from yesterday that I said that when there is eccentricity damping, so the eccentricity is damped with a given time scale, the semi-major axis exerted, the migration exerted by the disk is not just the normal migration term, but there is this additional term related to the eccentricity of the planet. There is an extra force for migration. So when I am here at the equilibrium point, the migration rate, the nominal migration rate of the planet cancels the damping term. But this term remains. And this term depends on the eccentricity. And when you are on a libration, the eccentricity changes from one side of the libration to the other side of it. So even if on average this term is cancelled there, it's not cancelled on the extremes. And because the amplitude of this term is proportional to the eccentricity, there is a negative damping of the semi-major axis, which is higher here than here. So the damping of the semi-major axis in this side of the libration tends to shrink the libration. And the damping of the semi-major axis on this side of the libration tends to enhance the libration. And because this is larger than here, then on the sum of the two forces is that the libration amplitude increases until the body escapes from the separators, which is what we have seen before. This is, of course, a very hand-waving explanation of what happens, but one can figure it out mathematically what happens. And in particular, this has been the original paper that has pointed out that this process can occur, and this paper is probably the most complete treatment of overstability. So what happens in mathematical terms is that the equilibrium point in which, as we have seen before in the diagrams, is surrounded by libration orbits in presence of dissipation is not a center, but it becomes a focus. And this focus can be stable or unstable, you need to compute the eigenvalues and to know if you are in the unstable case where the distance from the equilibrium point increases over time, or in the stable case where the distance from the equilibrium point increases over time. And so Deck and Batygin computed in which cases the planets are stable or unstable. And they summarized their results for each resonance, for instance, P22 and P21, on a plane where on the y-axis you have the mass ratio, mass of the inner planet over the mass of the outer planet. And on the x-axis you have the eccentricity damping time scale of the inner planet versus the outer planet. And the boundary between stability and instability is given by a curve like this. And these curves depend on the total mass of the planetary system relative to the star. So green is if the sum of the masses of the two planets is 1/1,000,000th of the star, magenta is 10⁻³ of the star. If the disk is uniform, the eccentricity damping and the mass are related, because the eccentricity damping is proportional to quantities of the disk, okay, and it's proportional to the planetary mass. So if your disk is uniform, you can say that aspect ratio and density are the same for the two planets, and what changes between the two planets is just the mass. In that case, the planets have to be on this diagonal because the ratio of eccentricity damping is anticorrelated with the mass of the planet. But in a disk that is strongly ununiform, then you can have different. In most cases, you are on this line. And so what does this mean? That you are unstable only if the inner planet is less massive than the outer one. Because if the inner planet is more massive than the outer one, you are always in the stable region. And if the planets are relatively big, the inner planet must be significantly smaller than the outer one, because you cross the stability boundary 10⁻⁻⁴. For the 2 to 1, it's a little bit worse. So if the planets are very small, you can have overstability also in the case where the inner planet is a bit more massive than the outer planet, but less than an order of magnitude. There can be no overstability in outer resonances, and this is because we reverse my scheme. So now the semi-major axis damping due to the eccentricity term is stronger on this side than on this side, because the eccentricity is higher here than here, which means that this force, which shrinks the libration amplitude, wins over this force that tries to expand the libration amplitude. So if the smaller mass planet is in the outer resonance compared to the inner planet, more massive planet, there is no overstability. Overstability can also be quenched at the planet trap, because at the planet trap, we have the co-orbital torque that kicks in. And this co-orbital torque has to be a strong function of the distance of the planet from the trap, right? Because if you are a little bit outside of the trap, then the co-orbital torque is too weak compared to the normal libration torque, which is also called the Lindblad torque. I tried to avoid that name yesterday. It is in the slides today. And if you are inwards of the trap, the co-orbital torque has to be positive and stronger than the migration torque. That's why the trap works. So that means that the semi-major axis equations are modified by this term with a strong beta that so enhances the positive torque of the semi-major axis as soon as I go away from the nominal location of the trap. And thanks to this term, then these vectors can be changed. So this vector was stronger here because the higher eccentricity, but we are now inside of the planet trap. And so we have this positive term that becomes strong, that does not exist on the other side of the trap. And so now this vector can win over this other one and lead to a libration shrink rather than libration expansion. So overstability at the trap, provided that the trap is steep enough, so beta is big enough, is also quenched. This is the paper that we have in the lunch. Altogether, you get this kind of picture. So what is this? This is for two planets of 4 and 8 Earth masses, for instance. This shows it's the collection of numerical integration. And the colors show in which resonance you are trapped as a function of two parameters. One is the migration rate normalized to the orbital period, away omega. And one is this ratio between the eccentricity damping and the semi-major axis damping, which can be typically between 100 and 1,000. But you can imagine if the disk is very thick, it can be even less than 100. That's not very often. And then you see that the planets which start far away can be captured in 3:2 if you are in this part of the diagram. But if you fail, if you're not here, you fail capturing 3:2, you are capturing 4:3. But if you are in this part of the diagram, you fail also 4:3, you're capturing 5:4, and so on, up to 7:6. 7:6 is the last resonance that can capture this planet. Beyond, it's only a chaotic sea. And so you are captured into the more distant resonances if your migration time scale is long in orbital periods. So this number is low, is high, and you are captured in high or resonances with a high K, like 7:6, if your migration is fast. And the boundaries are not, well, a little bit irregular because of chaos, but clearly they follow some trend. And the trends are simply to understand. So these lengthened trends, this is the damping instability. So when the damping becomes strong, too strong, and the equilibrium point is rotated too much, and capture is not possible. The region where the lines are vertical, it's the adiabaticity criteria. So you are captured only if you migrate more slowly than the libration period time scale. And then the bottom here, in which you enter into this chaos, is due to the overstability criterion that I mentioned before. So this was done for these kinds of planets, because these planets correspond, these masses correspond to a system that exists, which is called Kepler-36. And we wanted to, this Kepler-36 is in the 7:6 resonance in this configuration. So we wanted to understand how it's possible the two planets skip all the other resonances and go into this 7:6 resonance. And this is the answer. So to be captured in 7:6 and not in all previous resonances that have been encountered, you need that this number, the migration time scale, is normalized to the orbital period, is very small. And this product, given the migration formula I gave yesterday, is inversely proportional to the surface density of the disk times r squared. Surface density of the disk decays like 1/r, 1/square root of r, or something like that. So this number is a decaying function of the distance from the star. So if you want that this number is small, you need to capture far from the star. That's the point. And if you want that this number is big, you can be close to the star. And so to capture in 7:6, this number has to be really small. And if you use some more reasonable disk model, I will not detail, then this shows that capture in 7:6 is possible at only at distances exceeding the astronomical unit. So the point of this paper that we are publishing is that at least in this case, we can say that these planets have been captured far away, and then in resonance, they migrated close to the sun. Because in general, when you see planets in resonances, it's obvious that they migrated. It's the only way to go in resonance is migration. They had convergent migration. But you don't know if the planets have been captured far away from the star and migrated along a large amount, or they have been captured, they formed already where they are, more or less, and just migrated a little bit and got captured in the resonance. So in this case, we can say with good confidence that the planets have been captured far from the star and then migrated together close to the star, because otherwise they would have been captured in resonances like the 3:2. But this is a very specific case. There are only two planetary systems in such a resonance like 7:6. And so in the other cases, maybe the planets have been captured closer to the sun. Okay, so everything I said so far concerns 2 planets. But in principle, you can have more than 2. So let's do again the exercise with 3 planets. And again, we normalize our units to the inner planet. And let's see what happens. So both the second and the third planet migrate in compared to the inner planet. And then the second planet reaches resonances first. So the first 2 planets capturing resonance, but the third planet is still far away. Then the third planet approaches the resonance also, and then also goes into resonance. And now we have a resonance with 3 planets. Each planet is in a mean motion resonance with the next. And the system, as you can see, stabilizes again. Each planet is in resonance. They don't approach each other anymore. The eccentricity reaches an equilibrium. The eccentricity of the inner planet is goes higher because this planet is squeezed in 2 resonances from the inside and from the outside. The push in eccentricity is stronger. We can go to higher eccentricity. But at the end, we have what we call a resonant chain. And you can add more planets and build resonant chains with more planets. So this is an hydrodynamical simulation showing a system of planets of super Earths that form beyond the snow line and they migrate towards the inner edge of the disk. So just to show what happens when you have a large number of planets. So the planets overall, they all migrate in. There was one planet that temporarily migrated out and in a temperature-related rotation torque, which I said yesterday, it's only temporary. So they go to the inner edge of the disk. The first planet is trapped at the planet trap at the inner edge of the disk. It tries to hold the other planets in resonance. This works for a while until new planets come in. So there is more push. The resonance chain is longer. So this brings the planet to become unstable and merge. So the number of planets reduces and the masses go up until a new resonance chain is found, and this is stable. Is there. So migration, you can put in as many planets you want. The planets will arrange each other, merging if they are too many to be stable, until they simplify the system enough to build the resonance chain at the inner edge of the disk. Now, these resonance chains exist, they are observed, and this is a table of known resonance chains established by a number of authors in 2021. Now it's 2026, the list is much longer because tests have found several resonance chains. So resonance chains exist. And these are the resonances involved. You see 322, 43, 221, 53, 2, and so on. And the fact that some resonance chains exist is an undisputable proof that planets migrate, because it's the only way to make planets resonance. But resonance chains may not last forever. So as long as the disk is there with its push and damping, the resonance chains tend to be stable. But once the disk goes away, the resonance chains may become unstable. And this is a series of numerical experiments. So the planet, during the migration phase of the disk, have built up resonance chains which are fairly complex. So you can see many planets, 3, 4, 5, 6, and 10 planets in resonance with each other during the migration and damping phase. Then the disk is removed, and after a while, a few million years, the chain becomes unstable, and some planets merge and they become more eccentric. And a smaller number of planets survives, and they are not in a resonance chain anymore. So the instability can destroy the resonance chain and build a simpler system of planets, also fewer planets, more massive and more eccentric. Now the question, and indeed, when we observe the extrasolar planets, and we do a statistics of the period ratio between adjacent planets, we see that most of the extrasolar planets we observe are not in resonance chains. So during the migration of the disk, at the end of the phase of migration of the disk, the simulations build the systems whose period ratio distribution is like this. It's a staircase where each step is for a ratio of periods equal to a rational number like 76, 524, 43, 52, because these are the resonances in which the planet must be. But what we observe is this. there is a slight overabundance of planets close to the main resonances, but very slight and very different from this staircase. And in order to reproduce this, the observations, one has to conclude that most of the resonance chains become unstable. Not all of them, because we see few, but most of them, 95% of the resonance chains become unstable, because after the instabilities like this, the period ratio distribution that we get in the simulation is like this. There are two curves because it's two series of simulations to show that not very model dependent, the results are fairly robust. And so the observed distribution is a combination of this distribution and this distribution, with this distribution weighted by 95%. So most of the resonance chains, in all evidence, have to disappear, have to dissolve, become unstable. And the question is why? So Matsumoto in 2012 did a very detailed and controlled series of experiments. And so they built resonance chains by migrating planets one against the other. And then they removed the disk and they simulated how long the chain is stable. And they simulated for 100 million years, 200 million years, and decided if a chain becomes unstable before that time or after that. So they built diagram like this. For instance, for a 7 to 6 resonance, right, they found out that as long as you have 3 or 4 planets in the resonance chain, after you remove the gas, the chain is stable forever for the integration time span of 200 million. But if you have more than 4 planets, like 5, 6 or more, then all of a sudden the chain becomes unstable once the disk is removed very quickly, in a few million years. So there is really a threshold, a critical number of planets possible in that resonance, which in this case is 4. Then they repeated the same exercise for different resonances. So for different index, for different resonances, like 7 to 6, 8 to 7, 6 to 5, and so forth. With the planets have the same mass and they have some mass. And so they reported the results, the critical number of planets in resonance, as a function of how separated are the planets in resonance in terms of their mutual Hill radius. And the Hill radius is proportional to the mass of the planet to the power 1/3. So as you can see, going from a loose resonance like 65, where you can even put 8 planets in resonance, to a narrow resonance like 7 to 6, you can put only 4. And if you go to 8 to 7, you can put only 3. And in the 4 to 3 resonance, you can put many planets. But if you increase the mass of the planets, then the Hill radius increases. So for a given resonance, the separation of the planets is the same. But of course, the separation decreases in terms of mutual Hill radius, not because the separation has decreased, but because the Hill radius has increased. So for instance, if you take the planet 10 times more massive, the 4 to 3 resonance, which would be somewhere here, very large K, and with a critical number of planets in the chain bigger than 10, goes here. So the separation is less than 5 mutually radii, and the maximum number of planets you can put in the chain is 7. And then if you increase the masses of the planet even more, you go down. So this is a whole set of numerical simulations that give a clear criteria, empirical criteria, of how long can a resonance chain be as a function of the planetary mass. And the question is to understand why. And so we have done in 2 papers some experiments where we build a resonance chain with very small planets, planetary masses, because if the planetary masses are small, the chains are very stable. And then we slowly, artificially increase the masses of the planets once they are in resonance until the resonance breaks up. The resonance chain breaks up. And we try to understand why it breaks up. And what we found is that, for instance, in a simple resonance chain, like 3 planets in 524, 524, but this is true in general, as we increase the planetary masses, the libration frequencies in the resonance chain become faster because they depend on the planetary masses. So these are the various libration frequencies measured numerically in Fourier analysis, and they become faster. But the synodic periods of the planets remain the same, because these are just given by the orbital frequencies, which don't change with the planetary. And in particular, so you have two synodic frequencies, which are the difference in the orbital frequencies of planet 2 and planet 3, and planet 1 and planet 2, so very fast. But the difference between these two frequencies, which is this one, is lower. And the instability occurs precisely when the fastest libration frequency equals this combination of synodicity. So the instability of the chain is driven by an internal resonance within the resonance. It's a secondary resonance between a libration period in the resonance chain and a combination of the synodicity. Now, the synodic frequencies can be smaller and smaller. A combination of synodic frequencies can be smaller and smaller the longer is the chain. So the N is the number of planets in the chain, K is the resonance index. So the final formula is this one. So the combination of synodic frequencies has a frequency that decreases if I increase the length of the resonance chain and put more planets in the resonance, or I take a narrower resonance chain, so I increase the index of the resonance. The libration frequency, on the other hand, is a function of the mass. In this case, the square root of the mass of the planets, or the mass of the planets to the power 2/3, depending on the eccentricity at which the planets are in the chain. And so what we concluded here is that this resonance, secondary resonance, is between synodic and resonant degrees of freedom, is encountered at lower masses if you increase either the number of planets in the chain or the index of the resonance. And therefore, the critical mass to reach this to have this instability decreases with increasing length of the chain or index of the resonance. So this was in this paper a sort of qualitative criterion to asymptotic behavior of the synodic frequencies and libration frequencies, and then Goldberg put it in more quantitative terms, so to be able to compute the stability threshold of chains in analytic estimates compared to numerical estimates of Matsumoto. And so these are the results. So we have different chains here of 3 planets, 4 planets, 5 planets, 6 planets. K on the x-axis is the index of the resonance. So index 6 means 6 to 5 resonance, and index 4 means 4 to 3 resonance, and index 3 to 2 resonance, and so forth. So these are resonances chains with 2 planets. So for instance, this is a 6 to 5, 6 to 5 resonance. These are chains with 4 planets. So this would be 4 to 3, 4 to 3, 4 to 3 resonance. This would be a chain of 5 planets, 3 to 2, 3 to 2, 3 to 2, so on. And then we report the maximum mass that the planet can have to make the chain stable. And as you can see, there is a very good match between the analytic estimate and the numerical simulation. So clearly, it's these internal degrees of freedom that become resonant with each other that set how stable, how complex a chain can be. And if the chain is more complex than the limit, because it's too long, planets are too massive, the resonance is too close, the resonance becomes unstable. And it is so for let's keep this for simplicity and say that what I showed so far, of course, is for systems that are very pure, like those that you generate in a computer, where you have just your planets interacting with each other and nothing more. Okay. And this, we studied and understood the limits for the instability or stability of resonance chains. But nature is, of course, much more complicated than the simple numerical schemes. So there can be other effects that I call external effects that can drive the instability of the chains. And probably these exist in nature because we've seen that so many chains become unstable, extrasolar planetary systems, that it's difficult to conceive that we have so frequent instabilities if just the criterion I showed were in play, because you can form quite complex resonance chain that would remain stable. So probably external perturbations also play a role. And there are a number of external perturbations that can break resonance chains that have been envisioned in the literature. One is planetesimal scattering that I will detail a little bit in the following, so that in reality, your planets are formed in a disk of gas and planetesimals. As long as there is gas, the migration is dominated by the interaction between the planet and the gas, but eventually the gas goes away and the planetesimals remain. The planetesimals can perturb the planets and lead to an instability, what I will show next. It can also be that the planets park at the inner edge of the disk because of the planet trap, but this inner edge moves outwards due to photoevaporation or expansion of the magnetic cavity. And so this forces the chain to move and can, in some cases, lead to instability. There are several series of papers by Liu about that. Tidal migration can do the same. Once the gas is removed, then there is a tidal force between the star and the innermost planet that can push the innermost planet in or out, depending if it is inside or outside for rotation radius. And in particular, if it's out, the resonance chain is compressed, and this can lead to instability. Planetary mass loss. We know there are a number of posters outside, and we heard yesterday that planets can lose their atmosphere by irradiation. And as they lose their atmosphere, their masses decrease. And so as their mass change, well, the vibration frequencies change. And then you can pass through some secondary resonances with the synodic periods, which leads to instability. There is a possibility also of instability due to interaction with a star which is inclined relative to the planetary system because of some reason. Could be magnetic interaction with the disk or misalignment with the disk. But you know, from the Rossiter-McLaughlin effect, measurements that indeed the planetary system may not be equatorial with the star. If this is the case and the star is rotating, has an equatorial bulge that is inclined with respect to the planetary plane, and this equatorial bulge, what does it do is that it takes the inner planet and tries to make it precess around the equatorial plane of the star. So the inner planet starts to precess differently and goes out of plane with respect to the other planet. And this can trigger an instability, as discussed in this paper by Spalding and Bach. Let's detail a little bit more about planetesimal scattering, because it's interesting and because we think it played a big role in the solar system. What is the process here? So there is no more gas, and there is only the gravitation and interaction between a planet and the planetesimals around. And this interaction, scattering, moves the planetesimals, but by an action-reaction principle, also moves the planet a little bit. Planetesimal is small with respect to the planet, but if there are many planetesimals behaving in the same way, their effect can add to the planet, and so the change in the planetary orbit can be seen. So how does it work? So let's consider a simple case of a planet and the planetesimal outside of the orbit of the planet. So here is the planet, here is the planetesimal, coordinates, same major axis, eccentricities. And these red curves are the boundaries within which the orbits cross and outside which they don't cross. So initially, our planetesimal is close to the planet, is close to crossing, but doesn't really cross. So there are two possibilities. Either the planet scatters the planetesimals out, and in reaction, it moves inward a little bit, or it scatters the planetesimals in, like this, and in reaction, the planet moves out. So there are some planetesimals which are scattered out, some planetesimals which are scattered in. Who wins? If all planetesimals are initially outside of the planet, clearly are the planetesimals scattered in that, are the planetesimals scattered in that win, because if the other planetesimals were winning, the planet would move inward and then would detach from the planetesimal. Whereas if the the planetesimals are scattered inward, the planet moves outward and can encounter new planetesimals. Because your planetesimals are outside the orbit of the planet. So clearly, if all the planetesimals are outside the orbit of the planet, the dominant scattering process is outside in, moving the planet out. But of course, you can only also have planetesimals inward of the orbit of the planet. And for planetesimals inward of the orbit of the planet, the dominant scattering process is inside out, which moves the planet in. And so in a uniform disk, again, who wins? Like yesterday for type 1 migration, right? You have the inner disk, inner planetesimal disk that tends to move the planet in, outer planetesimal disk tends to move the planet out. Who wins? And it has been shown in this paper by Kirsch et al. That the inner disk wins because the synodic period with respect to the planet, so the frequency of close encounters with the planet, is shorter with respect to the planetesimals outside. Even if the densities are the same, there are as many planetesimals outside and inside. Those inside encounter the planet more frequently, so they are affected wins. And so this is the result for a single planet in a disk of planetesimals. Again, a paper by Kirsch. The planet starts to scatter the planetesimals, creating these ears or tails, or called tisserand tails. But the inner disk wins over the outer disk. And so you see that the planet, which is signaled by this cloud of planetesimals trapped in the Trojans, as Trojans of the planet, moves inward here. And at the end is here, where it started. So a single planet moves inwards, and these are its migration tracks for different planetary masses for a given planetesimal disk. Various realization, because this is scattering, so it's all a little bit stochastic, right? And the number of planetesimals is a finite number, so you have some stochastic variability, but not too much, and the migration is equal. Single planet in a planetesimal disk moves. Now, what happens if you have two planets, for instance, and they are embedded in a disk? Well, it happens that for the outer planet, the planetesimals outside of its orbit are more important, because inside of its orbit, there is the other planet that is taking care of its own planetesimals. So this outer planet will tend to move out. And for the inner planet, the planetesimals are most inside of its orbit, because outside there is the other planet. And so the dominant effect for the inner planet is inward migration. So the two planets tend to migrate in a divergent direction. And if you have a resonant chain, like, for instance, Jupiter, Saturn, Uranus, and Neptune, you have a chain of planets, and you have a disk of planetesimals, then this is what happens. The planets always tend to separate from each other. The inner planets moves a little bit in, and all the other planets move out, but the planets separate from each other. The orbital periods tend to increase. And so this is the idea that Chatterjee and collaborators had to explain the lack of resonant chains, because initially you have a resonant chain, but if you are still planetesimals around, and this is a big if, there are still planetesimals around, it depends how this planet formed, migrated, we don't know. But if somehow planetesimals were around, this is an inevitable process. The planets move in divergent direction, so they are extracted from the resonant chain, and they are deposited at random locations, nothing to do with resonant ratios. So this can explain, and their paper explains, the period ratio distribution, for instance, without having exciting the eccentricity. So this is a valid process if there are planetesimals. And now to finish, what do we think happened in the solar system? So in the solar system, we have two categories of planets, the terrestrial planets and the giant planets. The terrestrial planets are small, so they did not migrate much. And in addition, we know that it took a long time to form. Mars formed quickly in a few million years, but it's Mars is the 10th on Earth mass. The Earth took 50 million years to form, at least, maybe even 100. So completed its growth well beyond the disappearance. So for terrestrial planet, migration is not a big issue. They were very small during the gas. But the giant planets are giants, very massive. And they were massive when the gas was still around, because they captured the gas from the disk to become giant planets. So for the giant planets of the solar system, migration is an issue. And so all the giant planets of the solar system must have migrated. And the question is, why are they so far out? So I gave a first hint at the end of the lecture yesterday, when Saturn migrates faster than Jupiter, and when it catches Jupiter in resonance, the migration of Saturn and Jupiter stops. So I don't know where Jupiter formed, but provided Jupiter formed, so this scale is sort of arbitrary because we started the planet at 5, so its migration is stopped at 3, but the planet could have started at 10 and stopped its migration at 5. So you don't know. But the Jupiter and Saturn stop their migration when they go in resonance. Uranus and Neptune form somehow beyond, and they also migrate even faster because Uranus and Neptune are in type 1 migration, Jupiter and Saturn type 2 migration. So they approach Jupiter and Saturn, and they have also to go in a resonance. So in our solar system, we must have had a resonant chain of the giant planets at the end of the gaseous phase. It's inevitable. It's the only configuration that the giant planets could have acquired in the disk. And thanks to this block of migration due to Jupiter and Saturn, this explains why Jupiter did not come to 1 AU like most of the extrasolar giant planets, or even become a home. But now we have a resonant chain, and today we don't have a resonant chain. Right? So it means that the planets were in a resonant chain, very compact, all together between 5 and 12 AU. Right? But now the planets are not in a resonant chain. They are much more separated. Neptune is at 30, Uranus is at 20, Saturn is almost at 10. So what happened? Right? How can we explain the current orbit if the original orbit at the end of the disk of gas was a resonant chain? And the idea is that, okay, this chain became unstable. And this is the basic of the NISER model. So it started in 2005 and evolved towards resonant chains in 2007. So the idea is that once the disk disappears and the disk of gas that holds this chain together, we have a disk of planetesimal. And this disk of planetesimal is beyond Neptune, is the ancestor of the Kuiper belt, contained something like tens of Earth masses, 10, 20 Earth masses. And then you have an interaction between the planets in the resonant chain and this disk of planetesimal, which we think were all beyond Neptune because the planetesimals in the giant planet region have been consumed by the accretion of the giant planet. And so let's see what happens. The planets interact with the planetesimals, stirring them up. In return, at some point, they are extracted from the resonance, and this leads to an instability. The resonance is compact, so when planets leave the resonance, they start to encounter with each other. And this excites the eccentricities of the planets, scatters the planets away. Uranus and Neptune are scattered in the planetesimal disk, so the planetesimal disk is dispersed, and this is what damps the eccentricities of Uranus and Neptune to 0 and place the planets at their correct location, more or less, 20 to 30 U, leaving Jupiter and Saturn slightly eccentric beyond. So this, we think, is what happened in the solar system. So a resonant chain became unstable, as we see happening in most of the cases for extrasolar. So let's close here. So these are my takeaway points. So resonances are periodic orbits, and they behave like a pendulum. So if you're not exactly the resonance, you oscillate around the resonance, back and forth around this equilibrium point. Convergent migration brings the planet in resonance. Divergent migration skips resonances. So resonant trapping fails if migration is too fast. So the time to cross the resonance is shorter than the libration time. Or if the eccentricity damping is too strong, or in case of overstability. But it doesn't matter, because if the planets are still in the disk and the resonance become unstable, they skip the resonance and they continuously migrate until they find another resonance which is more robust. And eventually you find a resonance that is robust enough. So eventually the planets get trapped in resonant chains. And if anything, because by migrating at some point, they go to the inner edge of the disk where there is a planet trap. So a planet has to stop there and wait for the other planets to come in. So eventually the migration is always convergent because at the inner edge of the disk is stopped. So resonant chains are ubiquitous. They have to form all the time when there is the disk. And it's the only configuration in which the orbital period, the period durations among the planets don't change even if the whole system can remain in migration. So the emergence of the disk, planets should be in resonant chains. And some chains exist today, but most of the planets that we see today, solar planets, are not in resonant chains anymore. So there is evidence that these resonant chains have to become unstable, most of them. So in a simple system where we only have interaction among the planets, we understand what are the limits of stability, and they are dictated by these secondary resonances between libration periods and synodic periods. But in nature, it's much more complicated. There are planetesimals, there are tides, these can be dispersed in an irregular way. So there are other processes that can destabilize the chain. There is an interesting paper by Dai et al. That came out last year that they study with tests the occurrence of resonant chains as a function of age of the system. And they found that if you look at systems that are younger than 100 million years, resonant chains are very common. They amount to 50% of the cases. And it's only when you go to systems that are billion years old or later, the resonant chains are almost all completely gone. So it seems that it takes time to destroy these chains, but to be very fast. In the solar system, where we understand things better because of many constraints, we are pretty sure that giant planets migrated, ended in a resonant chain. That chain was responsible for the halt of inward migration of the giant planet, which is good for us, like some space for the Earth before. And that chain also became unstable. And any of the mechanisms I described can be invoked for this destabilization of the resonant chain, but most likely it's the interaction with the planetesimal disk, the ancestor of the Kuiper belt. And that disk existed because we see what remains of it in the Kuiper belt today, the scattered disk, and particularly the Oort cloud. Formation of the Oort cloud happens in the dispersal of this planetesimal disk at the giant planet instability. The Oort cloud, the Oort cloud, the source of long period comet, contains an Earth mass of material today, which means that this original planetesimal disk had to be few tens of 10, 20, 30 Earth masses at the beginning. So clearly with such a massive disk of planetesimals, planetesimal driven instability is definitely the most dominant. So we stop here. Yes, because there are formulae for that, and even at some point in the literature was even the debate of whether planetesimal migration can win over gas migration, which is not the case. So yes, there are. I don't have them here. You can look at the paper by the guy who did the thesis after Kirsch. I will give you the reference. And then there is the paper by Minton and Levison in 2014, where they compare planetesimal-driven migration to gas-driven migration, which closed the discussion whether which one wins. So there are general. Ladies first. Okay. Yeah, ladies first. Okay. In general, because of overstability. So because when the inner planet is less significant, less massive than the outer planets, it's going to overstability. The planets tend to rearrange and exchange of position. But it's not a firm rule. If the ratio is not too big, the planet can can be reversed over them. But typically, when you see the resonance chains that survive, the planets have comparable masses, like TRAPPIST. For example, planets have comparable masses. There is not a big mass station. But in general, you have a more stable chain if the planets are ranked with decreasing, because the outer resonance is more stable than. Yeah, yes. As I said, so when you skip a resonance, it doesn't mean that there is no resonance, that you go to the next resonance. And the resonance is that the planets become closer, become stronger, because the libration periods are faster. So for instance, the adiabatic criterion is more satisfied. Overstability becomes weaker. So already from 221 to 52, it's more difficult to go into overstability. In 43, it's even more difficult to go into overstability. So these are just ways in which planets eventually skip a resonance to go to the next. So at the end, the planets form a resonance chain. And if really they fail to trap in any resonance, they merge. And then you have one planet less, your system has fewer planets, bigger mass, and rearranges, it goes in resonance. So I've never seen in hydrodynamical simulation, or a simulation even embodied with migration forces, that does not end up in a resonance chain. Because this is the only final stable situation. Otherwise, the planets keep rearranging, being scattered, trying again, merging, and so on. And the only way is to block the simulation. So yes, you could have non-resonant chain system if the disk suddenly disappears in the middle of the action. But because migration is so quick, you've seen yesterday time scale of order of 100,000 years, and this is 5 million years. This is a sort of unsatisfactory explanation for the absence of resonance. So it's more likely resonance chain formed. Yes. Yeah, because it depends on it's by chance in some sense. So it depends on how the disk disappears. It has to disappear to preserve the resonance chain. It has to disappear neatly, relatively slowly, so that the resonance chain can accommodate. And there must be no planetesimals around in that system for some reason. So we published a paper in Nature Astronomy last year, 2 years ago, Picchieri et al., on how the resonance chain can be established in TRAPPIST. And there is another paper by Wang and Ormel. And it's amazing what must have happened in that system, because that system, you see the signature of the cavity, the magnetic cavity of the disk expanding a bit, and the planets that tend to stay attached to the outer edge of this cavity. And this, so it's complicated. I did not have the time to explain. So I think what happened for TRAPPIST is really exceptional. That's why these systems are so. Yeah, it's a good question. So in reality, because you don't have, so for a single planetesimal, yes, you can, if they can encounter lowers the eccentricity of the planetesimal, the eccentricity of the planet can grow. But if you have a swarm of planetesimals and you use argument of statistical mechanics, on average, the planetesimals become more eccentric and the planet is damped. So we can see actually this in this here. So you see, on average, the planetesimals close to the planet become more eccentric, apart from the planet, where they don't see the planet yet. And so you have a net growth for the eccentricity of the planetesimals, which damps the eccentricity of the planet. This is called dynamical friction. And it happens in stars and the galaxy and so on. Basically, the small bodies tend to become more eccentric, and the big body is sort of dragged and damped. You can interpret it as a sort of equipartition of excitation energy. And so because the small bodies are small, so they get all the excitation and they take it away, the excitation. So planetesimal driven migration, in summary, keeps the eccentricity small, but because planets migrate in divergent directions, they can cross resonances. In divergent directions, they can never be captured. But because of the scheme I drew, so when you have a planet here, this is the resonance, okay? When this planet migrates in circular orbit, encounters a resonance, it jumps out and comes out of the jump with some eccentricity. And then, of course, planetesimal scattering can damp it again. So you can have bursts of planet eccentricities when they cross resonances in divergent directions. And we think this happened in the solar system. We see trace of a jump of eccentricity of Neptune at some point. And this is when a block of planetesimals that were trapped in the 2-to-1 resonance with Neptune have been released, and they became what is called the kernel of the quasar. But okay, so these things can happen and they can leave some trace. If you know enough of the system, you can figure it out. Yes. Absolutely. Yeah. Yes, yes. So the planet, the moons of Jupiter, the first three, Io, Europa, and Ganymede, are a chain, 1 to 1 to 1 to 1 to 1. Three planets, 1 to 1. So clearly they enter the resonance by migration. For the satellites, there are two ways to migrate. Migration in the circumplanetary disk, when the satellite forms, that is towards Jupiter and can capture the bodies. But there is also a second stage, which is due to tidal migration. The satellites now are going out, so the tides will be. So they could also have been captured in tides, in resonances due to the tidal migration of Io out, captures Europa in resonance, and then the two go out and capture Ganymede in resonance. So we don't know, both are possible because they're all both convergent migration. And it's not really known if the resonance was established at the time of the circumplanetary disk or during migration or during more recent times due to tidal migration. It's debated. So why Ganymede is not? Ganymede is the last. No, Callisto, sorry, is the last. Why Callisto is not in resonance is not really known. Did it form too late and didn't reach the resonance? Were the 4 satellites in resonance and during the circumplanetary phase? Then this resonance chain broke, and then it recomposed during tidal migration, but only for the first 3, which are more affected by migration. This is a very likely possibility. And we had a full 4 satellite resonance chain at the beginning, broke up for one of the reasons I explained. So the planets are out of resonances, the planet Saturn are out of resonances, but then Io migrates out by tides, captures Europa, captures Ganymede, and wait an infinite time, they would capture Callisto as well. Did not happen yet. Yes. No, the rotation of the planet does not enter in this race. No. Then you can have spin orbit resonances and these kind of things, but these are resonances that affect the obliquity of the planet, for instance. In everything I described today, the rotation of the planet. Yes. Yeah, so these systems also happen where you have partial resonance chains. It's unclear. It's unclear what happened. Possibly an instability of a chain that was not complete, and some planets could survive right in the chain, and other planets have been. Yeah, yeah, of course. I mean, if you put planets very far from each other, then it takes a long time on migration to reach a resonance. But yeah, but migration is fast, so you tend to erase a little bit the initial conditions with the lifetime of the disk. But you could have also late formations, so that when the planet forms, there is not much lifetime of the disk to remain. Some of these systems can be also some planets form in the disk and migrate and capture in resonance, and then the planet that you don't see in resonance forms on a longer time scale out of what remains, like in a terrestrial, in the solar system. We're talking about a chain of giant planets, but we are not talking about a chain of terrestrial planets. So terrestrial planets continue to form after disk removal. So they formed in a natural way, in a non-resonant continuation. And so there is no mystery there. So in some systems, you could see the same, that planets migrated, got in resonance, and then destabilized other bodies, or other bodies left, and then they keep merging and fitting on longer time scale, and then they don't have any reason. So you have to analyze the system in a case by case basis. Yes, yes, sir. Yes, yes. The important difference is this one, because my scheme was simple, but not so wrong. So in a resonance of type k minus 1, the separatrices are open. And this is the resonant locus. So you can be captured in resonance without ever crossing the separators. If you take a resonance like the pi to 3, it's more like the first scheme I drew. So the X is eccentricity, this is the Keplerian location. And this is also the resonant locus, and this is the separatrix, and it closes. So when you come in, you encounter the separatrix. And then in my scheme, you understand that, so whereas this capture is certain, you are always captured in resonance. Maybe you can escape later, the conditions I gave are not satisfied, but you are always captured. Here you meet a separator. And so if you take my scheme, what happens here? So you librate and you migrate, and you have a combination of this. And basically you can combine this saying, okay, I migrate a bit, and then I librate, and then I migrate, and then I capture. But you can also say, okay, first I librate, then I migrate, and I'm out. Okay, so this is just to say that when you encounter a separatrix, the capture probability is not certain. You have a probability. You can, with some probability, be captured, and the complement of the probability jump across. And so these resonances capture much less. Nevertheless, with many planets trying, there are some which are captured in these resonances. They are rare, but there are resonances, like as we noticed in the resonance chains. Right? Yes. I think this is because there's the moon. So we see two kinds of moons around the giant planets. We see the regular systems and the irregular systems. The regular systems are equatorial, coplanar, circular, blah, blah. But they are very close to the planets. So I think that even when the giant planets became unstable and they had encounter with each other, their encounters were far enough too far to disturb the system. And then you have the irregular satellites. These are satellites that have all possible eccentricities, inclination, they are retrograde and so on. And these are sort of the analog of the Oort cloud. And these indeed are the population of satellites that have been perturbed by the encounters with the planet, and either captured during the encounters or randomized during the encounters. A little bit like the Oort cloud. The solar system is coplanar, including the Kuiper belt, basically. And then you go to the Oort cloud, it's a spherical reservoir of comets. The Oort cloud is 20,000 AU. It is a sort of mid-distance between the sun and the other stars. And that's where the effect of the other stars randomize eccentricities and inclination. The same occurs for the satellite system. If you have an outflow, you mean a jet from the star? But this is what creates the magnetic cavity, no? Isn't this what truncates the disk, the co-rotation? And creates the cavity? So in that case, yeah, it's the inner edge of the disk to which the planets stop by the orbital rotation torque. It's a planet trap. And this plays a role, right? The system of TRAPPIST, if you read that paper by Piquier et al., that the dominant role is this magnetic cavity and the expansion of the magnetic cavity. When it reaches the magnetic truncation radius, the material flows onto the star, but not on the disk plane anymore. It follows the magnetic field lines, and you have the polar accretion. No, nothing is neutral at this temperature. You're so close to the star. So you really are in the full MHD regime. I'm not an expert at all, but typically the idea is that you have the star here, this is your disk, then the gas flows in the disk, and then there are all these magnetic reconnect. And so you have an accretion channel and an ejection channel. And so here you have the one. This is the typical picture described by experts of MHD in this. I'm not an expert.